Right. So there is one other part of the, well, there's two other bits of the stats bit in your course. I've talked about the hypothesis testing and confidence intervals, which took up rather a lot of your time, but there was also regression, and there was also the bit on probability distributions. I'm just going to add a little bit to both of those, just so that I have at least, you know, sort of done it justice. So, if I can eventually get a pencil that actually has lead in it. Right. So, in your lecture notes, there is also another table after all the probability. You can go, well, continuous probability distributions. Lots and lots of them. There. I believe this also goes in your exam formula sheet. Is that correct? We've got several nods. I will take that as a yes. These are the different types of distributions that you have. What I would like to advise to you is that you should go and collect the examples you have of using those distributions into a little booklet of distributions and information about them so that you can keep them together in one place. So you may have noticed when you were doing your assignments that all of the stuff about these distributions is really spread out. Over here, on, you know, earlier on in your lecture notes, there might be the Poisson distribution, and then it doesn't mention the mean and the variance of that distribution until like 17, 20 slides later, after it's talked about other things. So you need to collect those things together. And you also, similarly to me drawing my little boxes and scale diagrams to help me choose what statistics goes with what, you need to know what situation these occur in as well. Because what happens is that there's the classic exam questions that says, you know, there's a light bulb and its lifetime is modelled by an exponential distribution, yes, with whatever it is, or it's a Poisson process with rate whatever, and then it asks you various questions. And it's almost always true that those questions have two different probability distributions in the one question, or at least like part A and part B are different ones because they are looking at the same situation differently. So you need to know exactly what those things measure because that's the most important thing for being able to do the things you need to do. So we're going to run through a little bit of that. Okay. Good. Okay. So on the list, on the screen, we have Bernoulli, binomial, Poisson, uniform, normal, standard normal, and exponential. They are the distributions that you have seen. And there is another secret distribution, which is the t distribution, which doesn't come up in normal probability questions, but comes up in statistics when you do t-tests. So there's one more distribution you've seen technically, which is the various kinds of t distribution. Okay. So the most important thing to know about any of these distributions is which of them are continuous and which of them are discrete. In fact, I might just go back to here so it's on the screen, on the recording. Bernoulli, binomial, Poisson are all discrete distributions. And uniform, normal, standard normal, and exponential are continuous distributions. So these top three here are discrete, and these bottom four here are continuous. That's important. It's important because Discrete distributions and continuous distributions happen when you measure different things. A discrete distribution happens when you count how often something happens. It comes about from counting something, whereas continuous distributions come about from measuring something. And so if you're looking at a situation where you have to distinguish what kind of distribution you need, the first test is whether it's discrete or continuous. Okay, whether it's counting or measuring. Let's start a new pencil, see if that will help. Otherwise I'll write in Texter. As I said earlier, this seminar seems to be cursed. That's not what I wanted to write at all. Okay, probability distributions. The first piece of information is discrete or continuous. And this means that you counted it, and this means that you measure. Okay. What is that noise? Okay, that's the most important thing you need to know. And then some distributions happen in some situations and some distributions happen in others. So the first distribution is the Bernoulli distribution. And that doesn't really come up very often, but it's definitely discrete. And you don't count really because the answers are 0 or 1. I can't control that, I'm sorry. The answers are 0 or 1. So a discrete distribution is asking the question of, when I have a single object, did something happen or not happen? That's what it's about. And happen is 1 and not happen is 0, basically. That's what the Bernoulli distribution is about. And basically there is a probability of it happening and a probability of it not happening. Probability of it happening is p, and the probability of it not happening is 1 minus p. That's a Bernoulli distribution. It's not particularly exciting. It would be like rolling a die and you go, did I get a 6 or not a 6? Or tossing a coin, did I get a head or not a head? Selecting a student and saying, is that student an engineering student or not an engineering student? That's what it's about. Okay, not very exciting. But the reason it has been mentioned is because from a Bernoulli distribution you can construct a binomial distribution. So your binomial distribution is also discrete. And the binomial distribution counts how many times something happens within a group. Okay, that's my way of saying it. And there are 4 things you're supposed to check, which basically are checking those things. All right? It's that it counts BINS. It's like you're counting how many successes there are. There are a fixed number of them. That's the size of the group. And you have the same probability each time, and they're independent of each other. You can look up those rules. But the idea is that if you have a specific group, and for each of the objects or people in that group you go, did it happen yes or no? 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 And you add up how many yeses there are, that's what binomial is. So the picture in my head is that for an individual, I'm going to draw them as people because nondescript objects don't look like anything. So it would be yes or no. This one has a 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 yes or no. Everybody's got a yes or no of their own. Maybe one more so it doesn't look quite so much like a grid. Okay? And each of those people, their individual yes or no is a Bernoulli distribution, with a 1 for yes and a 0 for no. But when you collect together the whole group of them, and you write the number of yeses, that's binomial. You know, 0, 1, 2, 3, 4, 5, 6 or 7. The number of yeses that I see out of any of those options, in my case it's 1, 2, 3, 4, that's a binomial distribution. Okay? So your binomial distribution is the possibilities for what could happen if you add up the number of yeses in a whole group of yeses and nos. So if I had collected a different group, I might have got a different number of yeses and nos, and I would have added them up differently, and there would have been a different probability of those happening. And there's actually a formula for what the probability of each number is in that situation. That's the binomial distribution, and you need to know that formula. So this table on the other screen tells you the mean and the variance and the standard deviation, but it does not tell you what the probability distribution function is, how to calculate the probabilities. I have a feeling that your exam notes thing will tell you that. Does anyone have a copy of what that looks like? Oh, awesome. That thing there has the formulas on it. So that's got an extra column from the one that's in the lecture notes. It has the probability mass function or probability density function that is different depending on whether it is a discrete or a continuous one. So that discrete ones, they have PMFs, and the continuous ones have PDFs, just so you know. Not that it matters. Each of those tells you about the probabilities of the events that are happening there. Okay. I will come back to that in a second. Oh, look at this. Did your lecturer do this? That's awesome. That's exactly what you want. Oh, look at his wonderful man. Anyway, so my binomial distribution is that you want to know what situation it happens in. So yeah, the fixed number of trials is great, but my addition to that is this lovely picture, because I think that's better. Okay. Sweet. I should say that sometimes binomial distributions come up when what you thought it was a continuous distribution. So I just want to point out to you that it could also happen is that everybody's got a number right, everybody's got a number of their own. And instead of recording the actual number for each person, we change that into, is it above or below some cutoff? So is it more than 5 for each of them? So this one's more than 5, this one's less than 5, this one's more than 5, this one's less than 5, this one's less than 5. And I might say, for the whole group, the number with more than 5, and now that's a binomial distribution, because I'm counting that we have 0, 1, 2, 3, 4 or 5 people who might be more than 5. So any time when you have a specific number you've got everybody got a number recorded for them, but you only care about whether it's above or below a specific number, then suddenly you're turning that number into a yes or no answer. So anytime for each individual there's a yes or no answer and you're counting how many times you get yes, it's binomial again. I want to warn you about that because it happens sometimes. Okay. The other distributions are the Poisson distribution, which is also discrete. And what I want to point out is how it is different from the binomial distribution. You've got this lovely thing here which says that the Poisson distribution happens when you count the number of events in a specified amount of time or space. That's exactly what it says. I want to compare these to each other. Something happens in time or space. Okay, so it's not, the key thing that's different is that you don't have a specific number of objects that you already know how many there are. In the other one there's a defined group, and each group has a number and you look at the numbers, or each group has a yes or no and you look at the yes or no's and you count how many there are. In the Poisson, the objects usually don't even exist yet. Okay, or they all exist and they're sort of just, you're looking at them at a specific range of time and things just happen here and here and here and here. And so it's more like the picture is this space of time and it's got, yes, something happened here, yes, something happened here, yes, something happens here. And you're counting how many times that happens. That's a Poisson distribution. It's still discrete because you're still counting how many times something happens, but you're counting how many times something happens across a certain amount of space or time rather than within a certain group. The object under study is a space of time as opposed to a group of objects. Do you think it's the air conditioning? Can anyone else hear that whine? Okay, good. It's not just me. And I have a feeling. Yep. Horace Lamb. It's got a better document camera than Flenchy, but basically everything else is crap. Used to be even worse than this, though. It had those awful tables that sort of flip forward, so that if you fell asleep, all your stuff would go under the table of the person, under the seat of the person in front of you. That was the old Horace Lamb. Back in my day. Okay. Really, I think one of the most confusing things for some people is the difference between a Poisson and a binomial. And the fact that sometimes a binomial comes up even though there's a numerical variable being measured. Your classic exam questions have a normal and a binomial, or they have a Poisson and an exponential. And so that's the only other one I want to mention. Your exponential distribution is the same situation as a Poisson distribution, but you're measuring something different. So in the Poisson distribution, you've got a fixed amount of time, and this is the beginning here. You've got a fixed amount of time and you're counting how many of these things have happened. In the exponential distribution, you're measuring how long it takes for something to happen. How long? How long does it take for that first yes to happen? Or anywhere, it doesn't have to be the first one. How long does it take to between two of the yeses? So that's what the exponential distribution measures. It measures how long it takes for something to happen. It's the same situation as the Poisson, but the Poisson is counting how many of the things happen. And so I should put that there, how many. And the exponential is counting how long. That's the difference between them. Right. And there are very few of them. They all have their own formulas for how you calculate the probabilities. The exponential distribution being a continuous distribution. And I know it's continuous because it measures something rather than counting something. It measures a distance in space or time rather than counting how often something happens. So, being a continuous distribution, its probability function doesn't tell you the probability of any one number. It tells you how likely it is to be more or less than that number. So, interestingly, this function here tells you how likely it is to be close to that x. It doesn't really tell you what the probability is at all. What you want to know is how likely it is to be less than or equal to a certain x. And that is something that you can add to this the moment you're allowed to write on your paper. The probability, the probability that your x is less than or equal to a specific value, a little x, is 1 minus e to the minus lambda x. Let's just check that. When x is 0, the probability of the time until something happens being less than or equal to 0, no, this is the greater than, is it? Yep, okay, no, that's good. Being less than or equal to 0 should be 0. It should be impossible to be anything under 0. And so if I put x equals 0 into there, I get 1 minus 1, which is 0. And the other option is to say, well, if the probability of being less than or equal to infinity should be 100%. You should get a number, which is less than infinity. So if I put infinity here, e to the minus infinity is 0, so I get the answer 1. Yes, I've got this correct. That is something extremely important to remember. You may instead remember this. The probability that the time, how long we have to wait, is more than a certain number is just that. That might be easier to remember. Up to you. So they're basically saying that the longer you wait, the less likely it is to wait longer. So the longer you wait, the more likely it is for you to see something happen soon. Well, at some point soon. Okay, that's the exponential distribution. And you'll notice that there are some times where it might say, if you're in an exponential situation, it might say, in a Poisson situation, it says, what's the probability of not seeing anything in this time? Or what's the probability, not that, sorry. Poisson situations can sometimes be exponential situations and vice versa. So there's this example where you can go, I'm in this situation, and I can say, what's the probability that x is... No, ignore that, it's just crap. I'm trying to come up with one, but you can say, what's the probability that I have to wait at least as long as 5 years? That's the same as saying with the Poisson that nothing happened in those 5 years, and so it's the same as P0 for the Poisson. And so this also happens to be, that's what I'm saying, happens to be the probability that my Poisson count equals 0, basically. So you can do either of them. Yeah. And the last piece of advice for probability distributions is that there are times when they ask you to switch your view. So I've mentioned it a couple of times, but basically beware that's a very vague thing to say, but beware of switching the view. I've done it twice already. When you switch your view from the individuals to the group, it goes from being a Bernoulli to a binomial. So the individuals have a Bernoulli distribution, but the group has a binomial distribution. When I switch my view from the number itself to whether it's more or less than 5, it goes from a normal distribution to a binomial distribution. When I switch my view from an individual to a group, the mean of a group, I'll be switching from like x, from a standard deviation of sigma to a standard deviation of sigma on root n. When I switch my view from how often something happens to how long it takes to happen, I switch from a Poisson to an exponential. Beware of switching the view. That's what I'm saying. And there was a classic one in one of the assignments where it has like, well, how likely is it for nothing to happen in 10 months? And then the next question was, how likely is it for nothing to happen in 15 months? And suddenly you have a new distribution because the Poisson is different depending on how long this space here is. And so every time you switch the view to a different object, or to a different time period, or to a different group of objects, you're going to have to change your probability distribution to something else. It's a very general thing to say, but sometimes that's a useful mantra to keep your focus in probability situations. And that's pretty much my major piece of advice for that. All right. I could talk about regression, but how long have we got? Oh yeah, I could. I did talk about regression. The very beginning of the other revision seminar online is about regression, and specifically it's about checking your assumptions, like all those graphs and stuff. And I think that I might leave it at that because people want to talk about these DEs and there's only so much time in the world. I may, if I have time later, talk about that, and I'll just add it on to the other recording. So I'm going to stop this one for the moment.